Hello. This time we're finding a closed formula for the Fibonacci sequence, and as you may recall, the Fibonacci sequence is given recursively by this expression here. Now, I'm going to write here, as I have here, a few terms of that sequence, and, well, let me reproduce what will be the effect of shifting the entire sequence to the left by one term. In other words, what we would have is something like this: f of n plus 1, right? So I'm going to shift everything to the left by one term. So it would be 1, 1, 2, 3, 5, 8, so and so on. Now if I were to repeat the same process and shift again one term to the left, we will get something like this: fn plus 2. Well, from this we have now 1, 2, 3, 5, 8, 13, so and so on. Now, something that we observe, right, by performing these actions is that if I add the first two rows, right, I obtain the third. First two rows, third. First two rows, third. First two rows, third. First two rows, third. So if I want to summarize this data, right, I can get a recurrence equation, which is the following. I have f of n plus 2 is equal to f of n plus 1 plus f of n. Well, I may rewrite this in the following equivalent fashion as f of n plus 2 minus f of n plus 1 minus f of n equal to 0. This is clearly a recurrence equation. Moreover, it's linear. So once we put it in this way, something that we observe is that we have in some way codified the shifts in the expression itself. So what this is saying, right, is that if you treat the entire sequence as a single entity, you may view it in this fashion. You say, well, if I shift twice and I subtract what I get by shifting once, and I subtract the original sequence, I get 0. Well, this entity that we have here is what we call the characteristic equation. Which of course is very much related to the equation, to the recurrence equation that we obtained just right here. Well, the beauty of this is that the characteristic equation is now a polynomial equation, which may be resolved, or when we may find the roots associated with it, by simply applying the quadratic formula in this case, for example. So in this case we get two solutions: S1 equal to 1 plus the root of 5 divided by 2, and S2, which would be 1 minus the root of 5 divided by 2. Now, but what is the resemblance of, or what is the importance of these roots to the original problem that we have? Well, in this case, the theorem indicates, the theorem associated with characteristic equations for linear recurrence equations is that in the presence of different roots, what you have is that every term of the sequence is given as a linear combination of powers of these two roots. In other words, we have that for each n greater or equal than 0, f of n is a times 1 plus the root of 5 divided by 2 to the power of n plus b times 1 minus the root of 5 divided by 2 to the power of n for some a and b. So now the only thing that we have to do is to find this a and b. But to find them, well, look, we have two unknowns. So what we can do is to obtain two non-equivalent equations relating these two unknown quantities. Well, how can we do that? Well, I can do this. Note that f of 0 is equal to 0, f of 1 is equal to 1. But this in turn must be equal to a times s1 to the power of 0 plus b times s2 to the power of 0. And on the second equation, I would have a s1 to the power of 1 plus b times s2 to the power of 1. Of course, we may rewrite this as a plus b, and this one as a times 1 plus the root of 5 divided by 2 plus b times 1 minus the root of 5 divided by 2. Well, from this, now we obtain a system of linear equations in two unknowns. Well, system of two equations in two unknowns. Okay, so from here, I've derived the following. And I would say, look, this equation is telling me that a is equal to negative b, or equivalently, that b is equal to negative a. So from that one, I can substitute this into the second equation to obtain the following expression. A times 1 plus the root of 5 divided by 2 minus a times 1 minus the root of 5 divided by 2 is equal to 1. Well, but from here, I can say, well, I can simplify the second equation into the following. And then from here, I can say, well, now I know that b is equal to negative a, and I know now that a is equal to 1 over the root of 5, so b is negative 1 over the root of 5. And with this, we combine all this data, and we get that for each n greater or equal than 0, we have f of n is equal to 1 over the root of 5 times 1 plus the root of 5 divided by 2 to the power of n minus 1 over the root of 5 times 1 plus the root of 5 minus the root of 7, minus the root of 5 divided by 2 times to the power of n. And with this we conclude. We obtain a formula that doesn't involve the recursive terms of the Fibonacci sequence. Take care.